Assalamu alaikum guys, how are you all doing? So today I'll actually be introducing ourselves to what we call the Laplace transform, just like the introductory part. Now what do you call Laplace transform? I actually love beta and gamma function, because at times you'll be given some certain questions, 0 to infinity also, but you look at it, but Laplace transform is always straightforward. Only if you want to apply it to some other things that you want to use the shortcut, because they'll tell you find the Laplace of this one, prove that this one is equal to this one. So literally you'd have known your focus much more that okay, this is a Laplace then. Now it tells that the Laplace transform of a certain particular function is defined by the what? By this integral. Just like the way if you are someone that is used to beta function, whenever you are being given a certain particular gamma function, they will tell you the what? The integral values. So let's move on to our normal main important thing today. So it says as what? Integrating as 0 tends to what? Infinity of what? An exponential function of the what? Of the Laplace transform of this certain particular function t dt. Then told us that s is a particular certain parameter that we assume to be a real number. And what are real numbers? You should know 1, 2, 3, and like that. So it says that the certain function of this particular real number would actually be equivalent to what? Or can be equal, let me just put it that way, can be equal to what? To the Laplace transform of the what? Of the function of t. And we know that what? The Laplace transform is defined with this particular integrating aspect. So therefore, it can be equal to this integrating expression. And what we just need to know is this as a normal basic person that wants to understand what Laplace is actually about. Then there's something into that we need to also call our attention to, is that what we call convergence. Now, whenever you want to talk about some certain things, you have to understand the convergence aspect of a particular integral values or integral expression. Does the value converges to a normal numbers, or does it tend to infinity? That means does it not even have solution, or it actually has multiple value? So under the convergence of Laplace transform, because whenever it is convergent, that is when the certain particular expression could be real. So if you look at the exponential function e raised to power negative st, they say this is actually the important aspect that contribute to the convergence of the what? Of this improper integral. This is an improper integral. So it tells that the function x, this function x, actually it tends to 0 and infinity, but this function x is just like something, when something is steady like snail, it actually is very, it feels remorse to just easily attain infinity like that. You get what I'm saying? So it keeps approaching it, just as s tends to infinity, it keeps approaching, but not just instantly move straight to infinity. The second thing is that you can have a certain, let's say that we have a particular certain a as a constant value, then such that the absolute value of this function of the x would be less than the what? The exponential, given the what? The constant of a with respect to x of the value. It says that for every large value of what? Of x. Are you guys what I'm saying? It says that the absolute function of x will always be less than or at times equals to the exponential what? Of the Laplace for every large value of x. So therefore, we can say that what then that means the function of s can be equals to what? In normal aspects, when we try to reverse it back, that means that we can say that the function of the s, just like what we said there, can be equals to integrating as 0 tends to infinity of e raised to power negative ax. Are you guys what I'm saying? Since we know that what? The function of x can actually what? Be equals to at times or less than what? The exponential function. And if you are to solve it into it, you have your a as a particular constant. And with respect to this, you have negative st, we have as. If you can see some little bit, what do they call it? Equality between them. So from there, we can see that what this expression is actually what? A is per negative as of the function of what? X dx. It will converge. And how does it converge? This is when the certain real value is greater than what? Is greater than a, which is a constant value. Are you with me? So it says that, and what? And the function also, we also have derivatives in order, and it must be derived. That means that if it can derive, it means that if you differentiate it, it moves on, it is being differentiated normally. That's the function of the x itself. And you have to know something that, like I said, f differentiation can occur under the integral sign. If you are there of what we call Feynman techniques before, you get that as DUIS, differential under integral sign. So just like what they're trying to express is that you can differentiate it under the integral sign also. So what do we, all these are actually just like a bunch of stories literally, but they help when it comes to some theoretical aspect of field. So let's move on to the important aspect of business. Yeah. Now let's talk about what we call linearity of what we call linearity properties of what? Of Laplace transform. And when you talk about, if you remember the Laplace value, we said Laplace of a particular certain function of what? Of the variable t. Now you should know that for every function of t, there is a constant value at the front. Even though it's 1, it is still a constant value. So we cannot say let us express it directly so that you can know. Are you get what I'm saying? So we say that Laplace transform is a particular constant value times the function of the what of the t could be equals to what, integrating as 0 tends to infinity. It's just like still the same expression we had done earlier, but just that what the k is involved now, and it's just like a normal constant value. Because if k is equals to 1, what will happen? You have your normal expression back. So, and we all know that whenever you are integrating, whenever you have a constant number, you do what? You throw it to the back of the integral sign. Then we have this where k is constant, just like a normal baby aspect. Now let's assume you have two certain particular Laplace transform. Let's say the Laplace transform is a constant times the function t, plus another certain other functions be a constant times another certain function, whereby Laplace puts them into brackets altogether. You should know that this is a clear intuition. You have the constant a integrating as 0 tends to infinity of your exponential function of the function of t dt, with the constant coming outside, then plus what? The same thing is applicable to b also. And in a nutshell, that means that we can say that what the Laplace transform of the function of a times that's a constant times the function of t plus a constant times the constant function of t could be equals to what? A, then Laplace transform of the function of t plus b, and the Laplace transform of the what? Of the function of the t also. So a and b, like I said, they are real numbers and they are constant. So at times they do call Laplace transform, we call it a linear operator. So let's check out a little basic elementary examples on these certain things, on its formula. How does it work? Let's see. Alright guys, from our basic aspect of what do they call it, of Laplace transform, from the introductory aspect, we want to try to test the basic expression, which is on the Laplace of the function of the t is equals to integrating as 0 tends to infinity of the exponential function, then of the function of the t variable, then dt. So we are trying to evaluate some certain values to test and to check out how the Laplace actually work. So the first one is when the particular certain function of t is equals to 1. So from that aspect, you know that the Laplace transform of 1 would be equals to integrating as 0 tends to infinity, right, of e raised to power negative st. Then this becomes what? You have 1. So that will become 1 then dt, which could actually be equals to integrating as 0 tends to infinity. Are you with me? Of e raised to power negative st then dt. So we need to evaluate this, and how do we go about that? From here we can actually say that let u be equals to negative st. So since we are actually differentiating with respect to t, that means our du over the t would be equals to what? Negative x. And do not forget, you know your normal basic substitution. If you have not learned some basic substitution and some things, don't fly to come to all these things. Now if you have from this aspect, now you have this point, you have negative s dt equals to du. So therefore your dt could be breaking down back as what? Du over what? Negative x, right? So from that aspect, you have this as the Laplace of 1 would be equals to integrating as 0 tends to infinity of now this becomes what? E raised to power what? U. Then dt becomes what? You have du over negative x. And do not forget, I tell you guys that this s is a certain real numbers. So since it's a real number, it's just like an expression of you, it's just like respecting, it's just like giving you a respect or a reference that since it's a real number, it can be thrown to the back. So from that aspect, you have 1 over negative x integrating 0 to infinity of e raised to power u, then du. And if you are someone who is not new to integral, you should know that if you are to integrate e raised to power u, because it will surely give you what? E raised to power u back. So from that aspect, you have this to be equals to 1 over negative x, then the value of e raised to power what? U, from 0 to what? To infinity. Are you with me? So from that aspect, moving on again, you have this to be equals to 1 over negative x. So we have e raised to power u, that's to infinity, minus e raised to power u, that's to 0. The bigger one minus the smaller logic under definite integral. So from that aspect of things, when you look at this, we can move this by breaking it down by saying, now if you have this, you know what is our u? You have negative st. So from that point, this is equals to 1 over negative x of you having e raised to power what? Negative st. Let me just put it this way, of infinity. I'm trying to break it down clearly. then minus e raised to power negative st of what? Of 0. Of 0. So from this point now, moving on, you have this to be equals to negative 1 over s. Then we sub infinity into the certain particular problem we have. So you have this to be equals to e raised to power negative s, then into bracket what? Infinity. Are you with me? Then minus e raised to power negative s times 0. So from this particular point, coming please, from this particular point now, we could actually break some certain things down by what? Moving fast. So from this point you have the Laplace of 1 to be equals to negative 1 over x. And if you guys could remember, like I told you, if you are someone that you haven't you don't have a solid background in all these things, please don't tamper with all these things. You won't like yourself, it won't end well. So make sure you learn the basic of things first before you move into all these things. It's very important. Now negative s times 0 gives you 0, and we know that what normal logic, anything raised to power 0 will give you 1. Then I have 1 over negative x into bracket. Now if you remember under exponential function of a particular standard value of infinity will still gives you what? Infinity, because e raised to power x is actually what? A certain large values. It keeps on moving like that, and it tends to give you what? Infinity. So the moment you have a certain value that gives you infinity as infinity, it's just like someone increasing in life. The moment you put a negative to the infinity, what happens to the function? It reverses back. So that means that we can say that was the function, and since we know that x is a real number, and for a real number it will actually be greater than 0. So for x to be a real number, even though this is tends to infinity, this can be 2 times any function or any variables you are being given. Are you get what I'm saying? So literally, since we can say this is tends to infinity, this is the normal real value, and in that point now, e raised to power negative of this particular certain variable will give you what? Irrespective of whatever they want to put there, it will surely give you what? 0. So from this point you have 0 minus 1, and that will be equals to 1 over x, then times negative 1, and that will be equals to 1 over x. So that means the Laplace transform of 1 will be equals to 1 over x. Alright, so we have the second variable, the second question. So from the Laplace transform of the function of t, we have to be equal to integrating as this of e raised to power negative st of the function of t, then the t. So since the function of t is k, we have the Laplace transform of k, which is a constant number, to be equals to integrating 0 to infinity of e raised to power negative st of k, then the t. How you get what I'm saying? So if you look at the rest of things that we have actually evaluated, from this point you can have this to be equals to k integrating 0 to infinity of e raised to power negative st, then what? The t. So in a nutshell, integrating e raised to power negative st, e raised to power negative st to the t will give you what? Will give us 1 from the recap of what we did earlier. So that means that what? The Laplace transform of k will be equals to k, and integrating e raised to power negative st dt from a certain point, that will give us what? 1 over x, just like you saying the Laplace transform of 1. Are you get what I'm saying? So that gives us 1 over x, and that will be equals to k times what? 1 over x, and that will be equals to k over x.